set theory, or sets. You can get rid of this word if it bothers you and just say we're going to talk about sets. And if you learned it in French, it's la théorie des ensembles. I think, yeah. Okay? And so a set is a mathematical object, which means it's an abstract thing. You can't like look in the world and find it, right? You can't see it. It's just it's an idea, basically. And a set is basically synonyms for set. You can think of a group, except a group is another kind of mathematical object, or a collection, or something like that. They all kind of give the same idea of individual items that are somehow brought together in some way. Okay? And so when we refer to sets, we sometimes use like a capital letter, like typically from the beginning of the alphabet. Like A is a set. I haven't told you what a set is, but I can say A is a set, and I can say B is a set, and I can say A equals B, which means that A and B are the same set. All right, so sets, we usually use capital letters like this. And then sets, the crucial relationship, the crucial idea of set theory is membership. So sets have members. Okay, so another way to denote sets is to use these curly brackets, or braces. Sometimes they're called braces, or curly brackets. Curly brackets. Okay, and you can think of them paired like this. It's important to get your brackets paired as kind of a container for a set. And so if I write something like 1, 2, 3, this is the set that contains 1, 2, and 3, and nothing else. Right? So the listing is exhaustive. So that's the set that contains 1, 2, and 3, and nothing else. Sets can contain anything. A, B, C. Okay? So in these two examples, I made sets that contain things of a certain type, but this is also a set. A set that contains love, Charles, and the planet Earth. So some abstract noun, me, and a planet. But anything you want, you can put into a set. They're just abstract things. Okay? So the primary idea of the primary notion is membership. Membership. So if we have a set like this, like the set, I don't know, let's use X, Y, and Z, then we can say something like this. X is a member of A. And we can say Y is a member of A, and Z is a member of A, or if you guys were saying it, you would probably say Z is a member of A, but I say Z. Okay? And we have a cute little symbol that looks like this. Let's see, Y is in A. So this means Y is a member of A, or Y is an element of A. So this comes from the Greek letter epsilon. So it looks a little bit like an E for element. So Y is an element of A, or Y is in A, or Y is a member of A. They all mean the same thing. And conveniently, you can have like equals, and you can have not equals, or we can have something like, I don't know, Q is not an element of A, just with a line through it. Okay? So this says the set A contains Y, set A doesn't contain Q, or Y is an A, and Q is not an A. Or Y is an element of A, Q is not an element of A. Or Y is a member of A, Q is not an A. Okay. So who hates math? Who has math anxiety? Okay, so far, have I said anything terrible? No? Okay, good. I've got to try harder. Okay. So let's just start with another set. B equals B is the set that contains, let's just take X and Y. Okay? So a nice thing about sets, or I don't know, another property of the sets, is that this set is the same as this set. So the set that contains just X and Y is the same as the set that contains just Y and X. In other words, the order in which you list things doesn't matter. Right? Now that's not true in general of, you might have seen things like ordered pairs in math, like, take 2 steps north and 3 steps east, right? The order in which you give those numbers matters. But with sets, the order in which you list things doesn't matter. But that follows from something we already said. is what we said is the important thing in a set is what its members are. So is X in Y? Is X in B? I look in B and I see X. So the answer is yes. So the order in which I list them doesn't matter. It's just yes or no. Exactly. And something else follows from that property, which is another way to write the same set. A very stupid way, unless you need some exercise or something, is to write, I don't know, it's the same set. It's the same exact set, because you can ask me, does this set contain X? And all I have to do is say, yeah, X is in there. Right? Does it contain Y? Yep, Y is in there. Nothing else is in there. The only two things for which you get the answer yes is X and Y. So there's no, so repetition is irrelevant to set. So order is irrelevant, meaning the order in which I list things in a set is irrelevant, and repetition doesn't matter. Okay? But these two things kind of follow from the fact that we said the only thing that matters is what's an element. Right? Order doesn't matter because of that, and repetition doesn't matter. You can say, is X a member? Yes. 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 You don't get anything new. The answer is that X is in the set. Right? So repetition doesn't get anything for you. So that's the crucial properties of sets, that they're these collection of elements such that something is either a member of the set or isn't, but the order in which you list them and whether or not you repeat doesn't matter. So we've said that anything can be in a set. So mathematicians are typically interested in sets of numbers, and they end up with interesting sets that give you lots of complications. We don't have to worry about them much. But let's take a set like this. So 1, 2, 3. So what does somebody mean when they list a set like that? They usually mean the set that contains 1, 2, 3, and keep going till infinity, or keep going forever, right? Right? Now, in that case, you can't list them all. You can't write them all down. Right now, if we had the set of we could have the set of Concordia students. And I could have Daria, and I could have Sam, and I could have Olivia, and I could have everybody in the room. And it would be a really big set. And I could list all the members of that set in principle if I had a lot of time. Or I could just say, the set of all Concordia students, and all 40,000 of you, or something like that. Right? So there's two ways to describe a set. By listing its members explicitly, or by giving some kind of description or rule or set of properties. Here, I kind of make it look like I'm going to list them, but I can't. This is the set of positive integers. Right? Or I could have done the even integers, or the odd integers, or all the integers, negative and positive, or something like that. But a set that has an infinite number of members, you can't list them all. You have to do what's called an intentional characterization of a set. Intentional characterization of a set, which is a way of defining a set by giving some kind of set of properties or a rule or a pattern, as opposed to extensionally listing all the elements. An extensional characterization. So this is going to come up in phonology. Let's always bring it back to phonology. If I gave you, let's say, you know enough about English. I say, here's a set of segments. So what are the members of that set? P, B, and M, and nothing else. Right? Give me an intentional characterization of that set. You know enough phonetics. Remember your basic articulatory phonetics? Are those the vowels? Are those the Cardinals fricatives? Are there fricatives? Yeah, they're the bilabial consonants, right? The bilabials. Just F and V are labial, maybe W. But they're the bilabials, maybe the tulips, right? So I could say the bilabial consonants of English. Right? So that's an intentional characterization. An extensional characterization is what I gave you on the board. I just listed them. Okay? So So sets can have a finite number of members, or they can have an infinite number of members. You can characterize a set extensionally by listing its members, or intentionally by giving some characterization like the letters of the alphabet, or extensionally the set that contains A, B, C, D, E, F, G, blah, 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 Z. If the set has an infinite number of members, you don't have an infinite amount of time. You've got to give an intentional characterization. And now I'm going to introduce you to a very, very special set. The most special set. It's a set that's so special you can derive like all of mathematics from it, basically. Actually, yes. And there's the special set. So remember, what determines the identity of a set? Yeah, what its members are. So ask me about some things, like is A in this set? Is A in this set? No. Ask me another one. Is L? No, I don't see it now. Right? So there's a set about which, no matter what you ask, I don't know if I'll be able to finish this sentence. Whatever you ask me, if it's in that set, it ain't in there. Right? It's the what? It's the set that has nothing in it. It's called, this is called the empty set. Or sometimes it's called the null set. Okay, so this is the most important set. This set has to become your best friend. So there's a few important things. One is that this is not the same as nothing. Nothing is nothing. That sounds kind of deep or vacuous. Nothing is nothing. The empty set is not nothing. The empty set is a set. It's the set that has no elements. Okay? So this here and this here are different. This is a set. And notice I said the empty set, or the empty set. Why? Because there's only one. Here's why. If I have two sets, A and B, and the set that contains A and X, and I say, okay, this set doesn't equal this set. How do you know that they're different? Well, since membership is all that matters, all I have to do is say, find something that's in one of them and not in the other. Okay? Oh, B is in here, but it's not in here, so they can't be the same set. X is in here, but it's not in here. They can't be the same set. Oh, even if I do this. B is in here, but it's not in here, these can't be the same. Right? But I can't do that with two empty sets, because I can't find something that's in here that's not in here. They're always the same set. So there's only one empty set. The empty set is the empty set is the empty set. Okay? There's only one. And, okay, this is where if you don't pay attention right now, you're going to miss points on your midterm. And I don't want you to. I'm going to try to trick you so hard. Okay, there's a special symbol for the empty set, which is this null symbol. This line with a circle through it. Okay? And this is not the empty set. This is not the empty set. Watch this. Watch what I do. Wait, I'm going to write it in red now. That is not the empty set. What is that? That is the set that contains the empty set. Because I forgot to tell you that the members of sets can be sets themselves. We'll get there in a second. That's the set that contains the empty set. Okay, so for your first quiz, write down another way to write this. This thing here in red. The set that contains the empty set. Another way to write it. You know everything that you need. There you go. So there's a set that contains the empty set. Right? Okay? And then you can have the set that contains the set that contains the empty set. Right? So what I forgot to tell you was that the members of sets can be sets themselves. So this set has two members. Let's call it capital C. C has two members. One is A, is an element of C, and another is the set that contains B is an element of C. Okay? So you could think of a set as a box. It kind of works. So think of a set as a box. And you stick your hand in the box, and what can you grab? Okay, I can grab an A. I can't grab a B, because it's in a littler box. So B is not an element of C. right? If you stick your hand in the C box, you can't directly feel B. The set that contains B, you can feel. There's another package, right? So you order your thing from Amazon or whatever, and they've got like your book, and then they got a box that contains your yo-yo, right? You can't feel the yo-yo because it's in another box. So the things you can grab are the book and the box with the yo-yo. So the yo-yo is not an element of the set. That's the way we're going to think about things. What about now? Is B an element of C? Is B in set C?
Yes.
But repetition doesn't matter. Why do you change things? Because it's not a repetition. In one case there's B, and in one case it's the set that contains B, right? So now B is. Okay? All right, so sets can have sets as their members. So you can have a set, you know, like I could form you into groups in the class, right? I could have the groups of, you know, the nice people, let's say Charles and Daria and Olivia, and then the naughty people, the rest of you. Let's see. We have the nice people and the naughty people, and their sets, the two sets that are in a set here. So this set doesn't contain anybody. It contains no people. It contains sets that contain people, right? It's kind of like the United Nations. You're Canadian, Canada's part of the United Nations, but you're not part of the United Nations, right? You're not a member of the United Nations. Canada is, right? So it's kind of like that. Your set, being a member of this set doesn't make you a member of the outermost set. This is where the box analogy kind of fails, because if you're in the big box, if you're in this little box, you are in the big box. But mathematically, we can't grab Charles by reaching into this set. We've got to go one level deeper. So if we have two sets, A and B, we have a relation between them. This symbol says A is a subset of B. Okay? And this is a very intuitive notion. I'm just going to say it first. A is a subset of B. Remember, everything is about elements. A is a subset of B if everything that is in A is in B. And there's nothing extra in A. So everything that's in A is in B. That's fine. That's all. Stop there. I said too much. So let me give you some examples. If A is this set, and B is this set, okay? Is A a subset of B? Yes. Because everything that's in here is in here. X is in here, X is in here. Y is in here, Y is in here. So A is a subset of B. How about this? Let's take sets T and S. Is T a subset of S? So here's T. It's got A and B in it, and C. And S has A and B and C. Is T a subset of S?
Yes.
Because everything in T is in S.
Yes.
Is S a subset of T? Yes. So, it turns out if let's take some other letters, if P is a subset of Q, and Q is a subset of P, then what do you know? If everything in one is in the other, and everything in the other is in the one, then we know that P and Q are the same set. Okay? Okay. Another way to say the same thing is every set is a subset of itself. Right? Every set is a subset of itself. Because every set has everything that's in itself. You notice that this subset symbol has two parts. It's got this part, which is kind of like a less than, and it's got this part, which is kind of like, this means less than or equal. That's this part here. Okay? And so, since a set can be its own subset, it's like less than or equal. There's another relation that we actually don't use that much with a simpler symbol, which is this. A is a subset of B, which is, I'll give you an example. Okay? A is a proper subset of B if everything A is in B, which is true, but B contains something that's not in A. Okay? Or another way to say the same thing is A is a subset of B if everything in A is in B, but it's not the case that everything in B is in A. So here's my set A, X, Y. Okay? Actually, let's do something easier first. Let's take so A equals this, B equals X and Q. Okay? So is B a subset of A? Prove it. Prove that B is not a subset of A. So if A is, yeah. Right, so there's an element of B that's not in A, namely Q. Good. So this is false. B is not a subset of A, right? Okay, now what about this? Is the empty set a subset of A? Okay, so yeah, that's what I have to do. I have to say this is not a subset of this if I can find something in here that's not in here. There you go. If we switch it, we say, if we can find something in here that's not in here, then it's not a subset. Okay? So what we do is we say we can't find anything in here. Therefore, we cannot prove that this is not a subset of this. And if we cannot prove that it's not a subset of it, we're going to accept that it is. Okay? So that kind of deals with your difficulty of proving that it is a subset. So what we do is we prove that we can't show that it's not a subset. All right, so it turns out for any set T, the empty set is a subset of T. Okay? The empty set is a subset of every set. Even if T is equal to the empty set itself. Right? Because every set is a subset of itself.